Okay, so I think we're starting to get everyone here. So welcome everyone to the Australian Regolith Geoscientists Alliance Specialist Group webinar. It's our first one for the year, so that's really exciting. We'll be getting a, if you're not already signed up as a member, it's only, what is it, $3? $1? It's super cheap. So it's not too late if you'd like to join our specialist group and you're not already a member. And we do send newsletters with lots of great news. We are going to be doing these webinars every month. So if you think you're interested in presenting, or if you have someone you think we really should present, please pass it along. Regolith, as you know, is everything between the sea and between the fresh rock and fresh air. So we really are happy to talk about anything regolith related at these webinars, whether it's from exploration and mining through to environment, groundwater, soil science, you name it. We'd love to hear from you and hear about your research or a current case study or a topic that you're working on at the moment. But today, I'd like to welcome Dr. Mario Iglesias-Martinez from Socioeconomic Minerals in Perth. Now, so Mario has been working for a long time in Supergene ore and in regolith. He has a broad range of experience across a lot of, shall we say, South America and Africa as well. And then obviously has been based out of Spain. So we're very lucky to have Mario here to present today. This is a long time coming. I know I talked to you about this, Mario, when I first met you. Was it like a year ago? So thank you so much for coming here today and presenting. So Mario is a research scientist, and this current topic is going to be really exciting, I think, for us because, one of the things that I think a lot of people who work in regolith are really aware of is that, land, the land, working in exploration and mining and working across these different types of landscapes, from geochemistry through to the geoscience aspects. There is impacts in terms of social, and there's also access. So it's been really interesting to see how this comes together. So I'll just pass over to you, Mario, and I look forward to hearing your talk. So thanks, Mario.
Thank you very much. Thank you all for attending this talk. Anna, for your kind words. My today's talk is about supergene deposits under an environmental, social, and governance perspective. And most of my research work has been focused on the exploration, characterization, and evaluation of supergene deposits. This has allowed me to observe that this type of deposits and mineralizations, sometimes considered as marginal, have received not enough attention despite their economical interest and the clear differences that they show in comparison with the primary equivalents. This work represents an initial approach to the study of supergene deposits from an ESG point of view and aims to highlight the importance of discriminating the supergene domain in defining strategies that can lead to a reduction in environmental impacts, also to promote principles like circularity in the mining sector and contribute with additional resources to the energy transition. The talk is structured in four main axes. I will start talking about natural stock and resource depletion. Second block is about technical and economical perspective. The third one is about environmental aspects. And the final one is I will talk about socioeconomic and geopolitical perspectives. As most of you already know, supergene processes represent phenomena occurring on the Earth's surface. They involve the circulation of meteoric water, which produces oxidation and chemical weathering of rocks and ore deposits. The combined physicochemical and biological activities can result in substantial enrichment of ore, potentially increasing metal grades by a factor of 2 up to 10. These types of deposits are typically accessible in the early phases of open pit mining and play a crucial role in the overall economic feasibility of mining operations. Consequently, there is a growing focus on exploring alternative sources of critical metals and metalloids to support emerging energy technologies. Let's talk now about the natural stock and the resource depletion. As the table indicates, supergene metal contribute notably to the world's supplies of base metals, such as copper, nickel, cobalt, structural metals, aluminium, iron, manganese, and to a less extent, precious metals. The table indicates the contribution of supergene sources to the global production. Nevertheless, the volumes are percentages indicated here are imprecise due to the frequent lack of clear definition of lateritic and oxidized domains when they are part of larger deposits. It has been quite tricky to get those data, but it's the best I could do. So, as can be seen in the table, some of these elements, such as aluminium or nickel, account for major percentages. The supergene sources of those elements accounts for major percentages in production. In the case of heavy rare elements, the extraction in Southeast Asia of these elements contained in the kaolinitic clays from the weathering of granites currently represent almost half of the global population, of the global production. Regarding cobalt and gold, while the percentages are lower, they represent additional sources to existing operations. Continuing with the natural stock and the resource depletion, which is a very interesting and controversial topic, we can say that a critical mineral supply is often uncertain, which represents a notorious challenge. This supply insecurity becomes particularly problematic as these elements grow in importance, especially in technologies aimed to mitigate global carbon dioxide emissions. The distinction between exhaustion and availability is critical in the implementation of strategic mineral policies. The preferred parameter to describe the stocks available will be global extractable resources, but this is impossible to determine due to our inability to predict what will be extracted in the future as technology and economics and social conditions evolve. Since criticality is a relative assessment, in many cases, there is not a right place to draw the line between non-critical and critical raw materials. And so the supply of all mineral commodities should be thoughtfully considered. It is noteworthy that not all metals are mined as primary or main product. Significant amount of metals can be contained in the ore as byproducts or co-products. Mining by and co-products represent an opportunity contemplated in the ESG policies as bringing numerous sustainability benefits related to risk mitigation, cost reduction, competitivity, and this is a frequent situation of supergene deposits, which represent a clear case of potential for multi-element sources. Wait a moment, because I have to change the configuration of my, okay, right. Regarding technological and economic perspective, there are large discrepancies in the forecast of needs for metals and minerals in the short and medium term. In the energy and digital transitions, they are huge. The challenge of ensuring a stable supply of mineral resources extends beyond the natural reserve that, in theory, could meet current demand projections. Technological improvements and metallurgical processes play a vital role. Let's talk about, for example, two examples, nickel and aluminium. In terms of the advances in aluminium metallurgical techniques, bring alternative sources such as nepheline cyanides, which are aluminium-rich rocks that, after being processed, produce inert waste, unlike the highly pollutant red mats produced by the bauxite processing. However, so far, the low aluminium recovery, estimated around just 50% through chlorhydric acid dissolution, doesn't appear to be a substitute for bauxite, at least in the short term. On the other hand, nickel laterites produces ferronickel, which is the primary source of stainless steel. but not suitable for lithium-ion batteries. Nevertheless, advances in leaching processes are starting to address this limitation. From an environmental perspective, vast amounts of power, water, and chemicals are used in the extraction and processing of ore, and the development of mining sites may disturb natural landscapes and ecosystems. Supergene projects are more superficial and tend to have low stripping ratios, in addition to be characterized by a greater rock friability and consuming less explosives. In principle, all this produces smaller carbon footprints. Regarding the water footprint, the question is not so clear, since those clay-rich materials possibly consume a greater non-recoverable water along with the tailings. Regarding post-miner rehabilitation, in tropical areas where most of the supergene deposits are located, revegetation is less of a problem than in arid areas. On the other hand, placement of tailings and disposal of effluent can be a problem in tropical climates due to the heavy rainfall and the low evaporation rates. In the case of nickeliferous laterites, energy consumption is often high, considering that the grades of the material are slightly above just 100%, compared to the 10% processed in the primary sulfided ore concentrate. This shows the need to find alternative leaching methods using more efficient reagents. Regarding rare earth elements, the environmental impacts vary depending on the phase of exploitation considered. Rare earths from kaolinitic clays have lower economic and energy cost for their extraction and separation compared to their primary counterparts, carbonatites and alkaline intrusives. However, in the processing phase, rare earths from clays have a greater environmental impact due to the use of strong chemicals and volatile organic compounds for lixiviation, and also higher water and power consumption. Regarding the iron ore, high friable goethite iron ore, compared with other iron ore types such as BIFs, represent a significant saving in terms of energy consumption, as the low silica content reduces drastically the crushing processes. Talking about gold, the supergene remobilization of primary gold in near surface has been an important phenomenon, liberating gold from encapsulating sulfide, enhancing gold recovery. Lateritic gold represents an additional source of resources, and the absence of sulfides also reduces the cyanide consumption, the generation of drainage, the acid drainage, and the release of metals in solution. And now let's talk about the socio-economical aspects. From a social point of view, it is extremely difficult to attribute any differentiating property to supergene projects. However, the development of supergene processes is concentrated in the equatorial and tropical belt, which largely coincides with undeveloped regions where mining activity carried out under the principles of sustainability is a prime developer inducer. In some cases, such as in the gold industry, extraction of supergene deposits requires less initial investment with conventional technology, providing opportunities for the development of small and medium-sized mining operations, supported by local companies, governments, and institutions. Chile and South Africa are good examples of how small-scale mining is institutionally supported. Exploitation of supergene deposits requires large areas and implies the possibility of affecting relevant sites, such as religious, traditional, or archaeological locations. In some areas, superficial oxidized deposits have been used as a source of minerals such as ochre, which is a vital ingredient in art and religious practices. The history of conflict between indigenous populations and industry in mining regions is well documented. And any mining project should contemplate from the very initial stage local communities in planning for those activities susceptible to cause impacts, including mining land rehabilitation and closure. It is well known that the global production of mineral raw materials provokes high level of tension in the markets. International monopolies, trade restrictions, and state-owned enterprises distort markets and undermine critical mineral supply security. The growth in demand supposes a combination of volatile prices, supply chain bottlenecks, and geopolitical concerns, creating risks for a rapid energy transition. In order to quantify the market concentration or monopoly of the most common supergene commodities, an economic index has been calculated based on fundamentally on the United States Geological Survey commodity statistics. This is the Herfindahl-Hirschman Index. Values of this index over 2,500 indicates high concentration and can be considered as anti-competitive situation. That means monopoly. As it can be seen in the table, cobalt, rare earth, and nickel lead the highest scores and represent commodities with elevated risk of monopoly for global supplies. Particularly concerning is the hegemony of production and refining of rare earths, which remains focused in China, where lower labor costs, less concern for environmental impacts, and generous state subsidies, leading to a national monopoly that could cause future supply constraints and also price volatility. As summary, it can be expected that in the future, alternative resources will be scarcer and will come with higher investments, especially considering the cost associated with the implementation of some environmental, social, and governance policies. Some estimation forecast that more than 3 billion tons of minerals and metals are needed to supply the energy transition. Supergene deposits can play a role as necessary additional resources, and improving its knowledge impacts on its technology efficiency. The careful definition of geological and metallurgical domains is a sign of project management quality, and the proper definition and characterization of supergene deposits help to increase efficiency across the mining process and help to predict its industrial behavior. All these aspects are necessary to implement specific and appropriate ESG policies based on their differences when compared with their primary counterparts. Yeah, that's all. It's a very short talk because, first of all, I am not an expert in environmental science, but working with supergene deposits, I realized that there is a gap in terms of the definition of domains. I have reviewed a lot of technical reports from mining companies, and it is difficult to improve and increase efficiency and reduce impacts if we don't have previously good knowledge about those type of domains, characterizing their differences in terms of geochemistry and mineralogy and processing, etc. They are very different in sometimes the same deposit. Comparing the oxidized, the primary and the superficial materials, they have huge differences that has an impact in all the mining chain. And because of that, I think it is a good starting point to first characterize this type of deposits and later try to diminish the impact and try to increase efficiency. So thank you very much.